The Being an Engineer podcast is a repository for industry knowledge and a tool through which engineers learn about and connect with relevant companies, technologies, people, resources, and opportunities. Enjoy the show.
You have a lot of freedom on the geometry you can produce.
Hello, everyone, and welcome to the Being an Engineer podcast. I am your co-host, Rafael Testai. Today, we got another very special guest, Hardik Kabaria, and he is a director of software engineering at Carbon. In this role, he leads the development of Carbon's design engine. He works on a variety of computational, geometry, and mechanics algorithms, including surface and volumetric parametrization, parametrizing topology changes, working with implicit neural representation of 3D geometry. And if by all means, as I'm reading this description, if the listeners are wondering what some of these terms mean, we're going to go over them, rest assured. Linear algebra-mixed-integer solvers, PDE constrained optimization tools, and physical simulations based on finite element framework. Before Carbon, he completed his PhD at Stanford University in the field of generating tetrahedral discretization for changing geometries and evolving topologies. Sounds like I'm going to be speaking with someone extremely smart. Hardik, welcome to the show.
Thanks for having me.
Absolutely. So why don't you tell us a little bit about yourself? How did you decide to be an engineer? What's your story?
Oh, how did I decide to be an engineer? I cannot even think of one sort of point in time where that decision may have happened. But very early on in my age, I was quite interested in paper airplanes. I remember having a book where there were like 100 different designs you could make. Made a sort of a project out of it, and that got me interested in being an engineer, especially something related to mechanical, aerospace. I didn't end up going in exactly any of those places. Fast forward, did my bachelor's in mechanical engineering in India, and that led to a master's and PhD here at Stanford. And I've moved around a little bit, started in mechanical engineering, then got interested quite a bit in computational geometry, did my PhD focused on that. And then the rest is history. Sort of became a software engineer in that space with Carbon since 2015.
Okay. So as I said before, I'm going to start defining your complex definition that you have on LinkedIn, your biography, piece by piece, so we can put it all together. So sure. You work at Carbon. Could you explain to our audience who Carbon is and what you do?
Sure. So Carbon is a 3D printing company. In a little bit more elaborate way, we have created a new fundamental way to manufacture parts within the realm of additive manufacturing, a new process. We call it digital light synthesis. So we create this hardware, which is the printer. We are the inventor of the process. And we also invent the chemistry, which are the resins that you can use on this printer to create parts. Sort of fundamentally different thing is our process is innovative, so you can print things significantly faster. These are all polymers, so plastics. And because we can print faster, we have allowed ourselves to use certain chemistry that enables us to create parts that have end properties. That means it's not just for prototyping, it is for manufacturing. Fast forward a few years, we have there are several out of our customers that are using our technology, sadly printer, resin, and the software that drives the printer all together to create parts like Adidas creates midsoles. And these are at scale in manufacturing environment, in factories, and these parts are real so that you can buy that from the consumer's website. Like you can buy the 3D printed midsole powered shoes from Adidas website. So that's in a nutshell company Carbon. We work at the intersection of hardware, software, and material science, as I alluded to before. My role is in software team. Within that, we early on, we realized that one of the ways we can accelerate how mechanical engineers find more and more applications that will be manufactured on our printer is we give them access to ways of designing for additive manufacturing. Just like you think injection molding is a manufacturing process is very mature, there are many software tools around the world that can help engineers design the parts that are right for that can be produced robustly with a high yield and without any error using injection molding. Our process is new, so it has its own constraints, it has its own freedom. So we wanted to create a design engine or design tool that specifically takes advantage of the manufacturing process that Carbon had invented. Even more specific, we thought lattice structures are these structures that are architectured that can lead to very phenomenal or fascinating mechanical properties compared to a foam or incumbent material. And so if we give access to these lattice structures as a metamaterials to mechanical engineers, they'll be able to design parts that will have superior performance compared to incumbents, and hence they might be interested in designing this way. So that started the idea of creating the product called Design Engine as we know today. I was sort of the first engineer on that team.
Before we go into that, I think that you just unloaded a lot of information.
Yes.
Can I ask you some follow-ups before we go into the details?
Please.
Okay,
please.
So if I understand correctly, just to recap, Carbon, it's a 3D printing company. Not only you make the printers, but you make a filament or a type of
resin. So our printer,
resin.
Yes, it's basically liquid resin, and that the printer shines a UV light on it, and that starts a chemical reaction that converts the liquid into solid.
Okay, and once it solidifies, you produce some very special properties. You said that could be used as soles of shoes. Is that right?
Yes. So this part is just about the process. So the process is rather, you can think about it in a very simple way. Wherever you shine the light, the liquid becomes solid. So our printer is basically a very fancy projector where the UV light is shining this light in a particular places where the liquid turns into solid. The beautiful thing about that is you have a lot of freedom on the geometry you can produce. That means you can produce really complicated geometry using this manufacturing method compared to what you might do with other traditional methods of manufacturing. So I'll pause there first, and if that makes sense, I can elaborate further on why lattice structures could play an important role in that argument.
That was actually going to be my next follow-up question because I design in SolidWorks and I use Markforged a lot here at teampipeline.us, where I work at, that sponsors this podcast. And we always think about the 45-degree angles that we need to use in order to avoid using supports in additive. So how is designing it for Carbon different than that?
So in some ways, it certainly is similar, that you do need supports if there are big overhangs or islands, as we like to call it. But our process is also a little bit more complicated because we have a pool of resin out of which you are pulling the part out. So you can create a lot of suction pressure. At the same time, there is heat being generated by this chemical reaction, so the parts could warp as well. So we have created design guidelines that is accessible to all the engineers in Carbon's ecosystem that help them design the part or maybe alter the design. So that's sort of at the high level. Yes, this manufacturing process, just like anything else, has its own constraints and it has its own freedom. The biggest freedom, I think, is just like you may have experienced with Markforged or any other printer, is that you can create very complicated structures. And one of the things that academics in this area has been excited about is lattice structures.
Lattice structures?
Yeah, and I'll define it a little bit. So lattice structures are basically a repeated pattern that you can fill the 3D area with. And each structure has a unique shape, right? So you can say a few cylindrical beams coming together is one structure. And depending upon the size of the beam, the angle of the beam, and the diameter and how they connect together, depending upon how much load you apply, it may perform or bend differently, right? So that's sort of our simple mechanics ideas. Given that 3D printing like manufacturing process we have can allow for very complicated structures to be manufactured, you can really take that idea to the town. That basically means you can define more and more complicated structures, and still the manufacturing process can successfully produce them at yield with the right amount of repeatability and all the other things that come with manufacturing process. So that has given a birth to this idea of design based on lattices. And by any means, I wouldn't say that Carbon is the one that introduced it. Lattice structure based design, I would say, has been studied in academia since 1980s. But it hasn't really led to a plastic product that is available specifically in consumer world, that is designed based on lattice structures and is available to people. So it's available to mass. That means it's manufactured at scale. So I would say that is something that Carbon did it first. The example is one of the example is the midsole that is created in partnership with Adidas. So midsole traditionally is done with foam. You have a foam that does the job of cushioning and giving support to the person that is running or standing or walking in the shoes. In this case, that foam part is replaced with a set of structures which are repeated structures. These are engineered structure. They're supposed to do a particular job. That means you can engineer them to your liking. You can say that if I compress it from the top, it's going to propel towards forward. So that means it gives you sort of a positive kickoff or a momentum or a boost. You can
Wouldn't that be
engineer
cheating in
them.
performance? In sports, wouldn't that be cheating? Just playing devil's advocate.
So 100%, I cannot talk about how a particular body of sports could think about performance of any particular product. As technologist, what I think about is what we want to do is you have a set amount of space, how thick a midsole can be, or how thick a helmet can be, or how heavy a helmet can be. Within that constraints, what is the best thing we can do? Can we create a superior helmet by designing the structures so that they are the safest, or they would reduce the linear or rotational impact the most? In terms of shoe, can it give the right amount of energy recovery? So yes, by any means, I'm neither expert nor I would say I have any authority to comment of what sports body would think about these products. But from pure engineer technology perspective, I think this is a fascinating area because we can achieve a better tuned mechanical properties out of a part to what an engineer might want.
I see. I agree with you. This is very interesting. I encourage all the listeners, if you're not driving, to quickly open up a browser and just type in Lattice Structure 3D printing or 3D printing Adidas shoes so you can visualize what it is that we're talking about here. I went to one of the biggest medical device shows called MD&M West just last month, and I happened to see the Adidas shoes that you're talking about with the printed sole. They were over $300. Is there something? Why is this technology so expensive, or it seems to be expensive? Is there a reason why?
So I cannot comment on the consumer price. So first of all, I'll make it clear that Adidas is a partner with which we help them make midsoles. At the end goods, the product which is the midsole and the upper and the final shoe that is sold, it is the product of Adidas. But you are raising one interesting question, is that when we replace these foam midsole with a lattice structure bed midsole, is it same at the manufacturing cost? Because that's something that we are really interested in. So 100% not. It is more expensive today. And partially is because of the volume and the scale. The scale at which the amount of material that is being consumed is still minuscule compared to the foam industry. And as we all know, up to a point, things get cheaper as more and more of the same material is consumed. So, and that is already, we see that happening already. That basically means we have the same material or the same raw material components being used across many different applications by several of our customers to produce lattice-based design, whether it's midsoles for Adidas, saddles for biking, helmets, and hence overall the cost of the raw material comes down, and hence slowly the same component will become cheaper, and so on and so forth. So that sort of expands the total applications or different mechanical components that can be made with the same technology, being the printer and the resin we have, and the software that aids mechanical engineers to design parts. At the same time, there's also the aspect of performance. It's quite possible there are higher performing shoes, higher performing helmets, and the companies that sell these goods might be interested in creating a premium segment. So, like I said, we do not go on the price, nor we influence it, what our customers sell the products at. It is their business. They understand each of these products and markets much, much better than us. We are a tool in that toolkit. What we extend them is yet on an innovative manufacturing process, at the same time an awesome way to design, so they can design parts that aesthetically look cool, that achieve the mechanical performance, maybe even one up than what they have been aiming to achieve, right? And do that very, very fast. So that means we try to reduce the time from the product conceptualization to the market, because in additive manufacturing, you don't have tooling cost or the tooling time. So that's sort of our vision and ideas.
Yeah, thank you for making the distinction between the pricing of Adidas and Carbon. Is two different subjects. I should have been more specific in my question.
That's right.
And also, when I said cheating, I should rephrase it to more of an advantage if one is trying to maybe propel him or herself forward.
As an engineer, I think about, you have the constraints, and within those constraints, everything I do is hope if I can make the lives better, whether it's for the athlete or patients, then it's a fair game. But anyhow, again, I have no legal authority or no sports body authority. Yeah, but it's a pure engineering mindset.
So I come from a biology background. My degree is in molecular biology and genetics, and now I'm working on my second degree in mechanical engineering. And this is why I'm going to ask you this question. It may come out of nowhere. I didn't even ask you this question before the podcast started, but it popped in my head. The grapefruit, if we look at biomimicry, which is used in nature as inspiration for engineering or any kind of technology advancements, they look at the pomelo, the grapefruit, and the skin of the grapefruit, the white part, is very thick. And scientists have used it to emulate it because it's a great shock absorber. And your technology of carbon, it kind of reminds me of the pomelo skin. Does it look to you like it or no?
Yeah, so that's certainly a good point. And I would say there is a whole field around it where people are actively trying to design stuff that is inspired from nature. And I'll give you some more example that has come my way as I have dove into lattice structures. Is you have woodpecker, and they have sort of a design around their brain that as they keep pecking the wood, it still protects their brain. If the same amount of torque or force or jerk was applied to human brain, it would suffer concussion. So clearly, there is a lot in the nature that we can inspire from and design. Quite often that we have seen is that the scale at which nature has packed engineering this design is amazing. What I mean by that is whether you take the skin of the fruit or woodpecker or any of these examples, it is very, very intricate design once you put it under microscope. And I do not think we always have the right manufacturing technology to create design at this high resolution. So that's sort of number one. We are slowly getting there. 100%. We have metal 3D printer that can print, not at Carbon, but in the world, where they can print at very high resolution. With Carbon, we are trying to sort of taking a step towards that. We are bringing a slightly higher resolution design availability for polymer products. By no means we are there, right? By no means. We are still in millimeter scale, but it still means that you can design very complex parts that may have that has inspiration from nature, and put those design in. And I'll give one more idea where our own design ideas have stemmed from. There are these polymers. It's called a blockopolymer, and there's a whole area that has studied these structures. These blockopolymer have phenomenal energy absorption properties, and there are scientists who studied their structures at nanometer scale. That has led to the area of triply periodic minimal surfaces. And what we do is take advantage of those and help them put in lattice structures at a different scale, significantly different scale, but they're still the structures that was actually found in other material is very useful at absorbing energy or postponing strain densification, and is helping some of our customer design very phenomenal parts. So you were 100% right there.
So when we look at lattice structure 3D printing, for those of you that are listening and maybe driving who have not had the chance to maybe look at a picture of that, I'm going to try my best to describe it. I think of it as like maybe a pile of toothpicks or something like that. Just how could you give our listeners a quick visual before I ask my question?
That's certainly one way to think about it. I was going to say you have a pile of toothpicks, but a very diligent engineer that is placing each toothpick nicely and is also maybe selecting toothpicks with different diameters and creating this web. But this web may look organic or may look stochastic, haywire, chaos, but it is not. It is engineered, and it is engineered to do a particular purpose, whatever that purpose of that product might be. And I would say that is in maybe a couple sentences what lattice design is.
Okay, very well said. So when I think of, when I looked online of lattice structure 3D printing, they all look like what we just described. So I think to myself, is there a disadvantage for looking that way and not being a traditional, maybe like a slab of 3D printing material? Imagine like a slice of bread, something like that, that's continuous, because it has holes in the material, right? When it's, what's the word we use? Lattice. It has the holes between it. Is it disadvantage or no?
Yeah, so I think it's both advantage and disadvantage. Like it would be miss if I say this is free. It's about, quite often lattice structures are used to reduce the weight. Like you don't need a full blob of a material for every task you need it to do, right? Imagine it's supposed to support some weight and not collapse. And you only have few materials to select from. So you're going to choose a material that is slightly safer side, so slightly an overkill. And at that point, you could choose to have a full slab of a material, or you can optimize for stiffness to mass ratio, which is most often we engineers do, even if we are not using 3D printing, right? With 3D printing and lattice structures, that idea has one more degree of freedom. That means you can choose the right structure and the right level of fidelity, right? Whether it's a big hole, small holes, is the same size of holes everywhere, same topology everywhere, to optimize the purpose, whatever is the purpose. And I may push back on this loaf of bread. Loaf of bread is not continuous either. It actually has holes. It's exactly like lattice structure.
You're right. It is a porous surface.
It is a porous surface. So it's actually a very good example for a lattice structure would be, but a very different scale than what we do for carbon.
All right. So I came across the term topology optimization, which it really caught my eye a couple of years ago. I'm someone that optimization really resonates with me. Even the way that I have things around my house, where I put my clothes in my room. Say, for instance, if I do my I'm almost finished with my example, but if I'm doing breakfast in the morning, I'll put my oatmeal next to my honey and next to the cinnamon in the same drawer because I know I'm going to do it all together. So topology optimization has been something that really resonated with me. And I wanted to ask you, is having perhaps a passion in topology optimization something that led you to where you are now? Is that how you started the journey?
I wouldn't say that. I would say I got deeper into topology optimization more during my work at Carbon. My sort of the way I came about here is more about geometry, processing geometry. And that was like creating tools for people who do topology optimization. So I'll give a very simple example. So quite often people make propellers. Propellers for engines and submarines and whatnot. So one of the things people have looked at for ages and they continue to look for is having the right shape of the propeller to do the job it's supposed to do. And this part of it is some idea of either topology or a shape optimization, right? And what I did during my master's PhD is create tools so that whoever is doing this job of optimizing, it's easier for them to perform physical simulations, specifically in the context of finite element analysis. So I would say topology optimization wasn't really my field. I wouldn't say I'm expert in the field even today, but I have had to go deeper into it as part of the trade.
Okay. Processing geometry. So if I understand this correctly, if you download a geometry into the software that you would make, I'm making a lot of assumptions here in a second, please correct me in everything I say, but if you download a geometry into a software that's going to optimize it for its purpose, how does the software know? Like, you're the person behind that codes everything?
Yeah, so geometry processing is sort of a wide term, and I'll tell what the term is, and then I'll tell you what we do at Carbon. You pick your favorite CAD tool. You draw, let's say, a few different objects, and you sort of Boolean them. So intersection, union, difference. You kind of create a CSG tree or a graph. Geometry processing, in a way, is what's happening behind the scene when you do that, right? Now that area is, I would say, up to an extent pretty well figured out, because you see SolidWorks, you name it, Creo, all of these tools very successful at entertaining the needs of a mechanical engineer in all the different industries. However, this problem is a little bit more complex when you start designing with even more complicated structures, where instead of having a 10 or 50 different beams, like this toothpick example in lattices, now we have 10,000 different beams. So the number of parts are significantly higher if you think about pure primitives in lattice structures compared to other traditional designs. And hence now the same geometry processing, you have to do it on a very different scale. You have to do it very fast, and you have to do it so that you can handle so many different parts. And that's sort of the job we do. So for geometry processing for us is doing those simple operations on primitive, but we want to do it for the type of designs that are often used in additive manufacturing, which often have like tens of thousands of different primitives instead of like 100 or 1,000.
Okay. Perfect. I wanted to take a quick moment to remind our listeners that the Being an Engineer podcast is brought to you by Pipeline Design and Engineering. Pipeline partners with medical and other device engineering teams who need turnkey equipment such as cycle test machines, custom test fixtures, automation equipment, assembly jigs, inspection stations, and more. You can find us on the web at www.teampipeline.us. And I'm here with Hardik, that works at Carbon. And I want to ask you, this is the story of how we found you. There's an article on a very famous magazine called Machine Design. You can find it on machinedesign.com. And the article talks about how you, there at Carbon, developed a viable swab prototype within a couple hours. So first, could you define to us, give us a visual, what do you mean by a swab? Because when I think of a swab, I think of like a Q-tip. What
Pretty
does that
much.
mean?
Yeah,
Okay.
and I was I had no idea what swab was either before this problem hit us. But as we all know, early on in the pandemic, there was a shortage of a COVID-19 test swab. And this particular swab, the technical term is nasopharyngeal swab. If you or anybody has gone through COVID-19 test, you sort of remember it as a not so happy experience. There is a swab that's pretty long, that goes quite a bit in your nasal cavity, and the person who is doing the test will roll the swab a few times in both the direction and try to collect a mucosal content, and they try to detect virus or viral content in that biological sample. The swabs, as I knew then and I still know, is a very simple object. But because the supply chain was broken, there was a shortage of the swab. And that led to one institute, specifically Beth Israel Deaconess Medical Center in Boston, to think about, can there be alternative swabs which are 3D printed, because the normal supply chain for the golden swab that is traditional is broken, and there is a shortage of it. That's where the problem was introduced to us and many other 3D printing companies as well. We started looking into it, like what swab looks like, what's the purpose of it, how does it function, and we did think of an idea that maybe we can design the tip of the swab using lattice structure, so that basically when somebody sort of rotates it around the axis, it will collect the mucosal content within it, and then you'll be able to pull it out and do the test as it is. We have developed this tool called Design Engine, which is specific for lattice design for additive manufacturing. We use the same tool to create this design, and we started printing prototypes on the printer that we have. So within days, we created a few prototypes, and we sent it out to a couple of clinical institutions where we got some feedback, like this thing is working, this is not working, this is how you might want to change design, and we started the design iterations for the swab. So that's sort of the rough story how we came about working on this project.
So before the original swab, is it cotton at the bottom, at the end?
Yeah.
Okay. For some reason, it just seems like it would be a little more painful to put a 3D printed swab, right?
100%. We all felt the same. The first design got the same feedback that the material you have is pretty stiff. It is not a pleasant experience. But we were able to iterate, and there are many different ways to create a flexible design, specifically using these ideas of lattices, even when the material is stiff. So we applied those concepts, and we went through those user studies to get to a place where the swab we designed went through a clinical study, and it was perceived as its equivalent experience. So it's not any worse than the golden swab, which is what was used at.
So changing subjects here. First, congratulations on that to you and the whole Carbon team for helping with COVID. So I've received, as I'm here in the middle of my second degree mechanical engineering, some of my mentors and advisors, and some of my mentors actually have been guests on the show. I'm very fortunate to have access to such high-profile guests. It's truly a blessing, and I share a lot of the tips that I receive on my personal LinkedIn. Everyone feel free to follow. But I've been given a tip that we should expose ourselves as mechanical engineers. This is what I'm training to become. To the more subjects, the better, because then we'll realize what we want to be, what we want our niche to become as we grow older and we specialize. How did you decide that you wanted to take this route of software engineering? Because if I'm not mistaken, your degree is in mechanical engineering, right?
100%.
Okay.
Yeah, I mean, I would say up till I was finishing master's, that was the path I was on. But when I started pursuing a particular problem in my PhD, the problem I ended up choosing was more about generating tetrahedral mesh as a discretization of a geometry to enable a particular type of physics simulations, right? And in that, there are two components, I would say. One is like coming up with the algorithm and the proof of the algorithm is going to work, which is more of a geometry concept. But it is not very useful unless it's implemented somewhere and it's usable by somebody. So just because I was in that area, it was evident that I had to learn to code the same algorithm that I came up with. And in geometry processing, speed is very important. As in almost every software gets measured on two axes, or every algorithm, like how fast it is and how robust it is. And robustness you can work on with theoretical concept, but speed you cannot just theorize. At the end, you have to code the algorithm and you have to run it on some computer or hardware, whatever, and prove that it is better on particular examples or what have you. So I would say I learned coding as part of that. And I still am kind of doing the same thing, if you ask me. So it is, to me, and a lot of our team members are also the same. Which degree you have is sort of less important than at Carbon, at least, than what you do with the knowledge you have and how you pursue it. So I would say, at least for me, it was an organic growth.
Well, that's a great snippet to use for maybe the introduction of the podcast right there. Jumping back to your bio, it says, well, this is almost fate, because I had electromagnetism class physics this morning, and my professor from physics said that linear algebra was single-handedly the most important math class he took in his entire career, and he encouraged us, everyone after this course, enroll in linear algebra. And what do I know? When I read your LinkedIn bio, it says that you use linear algebra mixed integer solvers. May I ask, how do you use linear algebra in Carbon and to solve problems?
Yeah, I mean, it's so many different places, but I'm going to give an example from this week. So linear algebra is basically a big field of study, and again, I'm not by any means the top of the world or even anywhere close to that to comment on it, but I'll tell you how we use it in geometry. a lot of geometry algorithms turn into a linear algebra problem. That basically means you will end up solving a linear system of equations. So you have a matrix Ax equal to B that you want to solve. You want to solve that very, very fast. Just this week, we do lattice population. That means we have a part and we populate with lattice. And within that, a problem turned into a eigenvalue problem. That basically means we have a lot of small 4x4 matrices, and we want to find eigenvalues of those. And those eigenvalues have a particular meaning, and that helps us produce a very good looking lattice. So yeah, linear algebra for us is sort of a very core bread and butter for the geometric related algorithms we design. And I certainly find it a fascinating area. It's very well developed. There are a lot of libraries out there to get started from. 100%.
Okay. What's something that I haven't asked you that I should have asked you?
Oh, that's a tough one. Not really something that comes to my mind. I would say if you are thinking about, like, as an engineer, what sort of is that important to me, like what skills to have, what skills not to have, I would say don't worry about that. Find the problems that you like and pursue it. I would say that has at least been my journey. I never thought computational geometry would have a career, and especially not in 3D printing. But it certainly was a good opportunity, and so far it seems a very rewarding opportunity. And if you are an engineer out there interested in exploring these ideas, then we certainly have a growing software team. You should reach out to us.
Okay. I want to dig a little bit deeper on that one. So don't worry about the skills. Find the problems you want to solve. That's very good advice that I heard before. Very reasonable. But then the follow-up is, how do you find the problems you want to solve?
It's very hard.
Right?
It is very hard. It is, it's very hard. And I would say the only way it often happens is through exposure. You talk to people around you, or look at the problems. As an engineer, quite a bit of us are hammer and nail, and totally I am like that. I had a hammer of generating tetrahedral mesh. So I went looking around for nail. And turns out 3D printing was one of those nails, and decided to apply it. That also works, but basically I would say expose yourself to a lot of problems, and something probably will appeal to you.
Okay. I think that's a wonderful message for all of our audience, younger and older. It's never too late to follow what problem you want to solve. And if they have any last comments for our listeners?
No, thanks for having me, and it's been a great conversation.
Of course. Thanks for joining us.
Thanks.
I'm Aaron Monker, founder of Pipeline Design and Engineering. If you liked what you heard today, please share the episode. To learn how your team can leverage our team's expertise developing turnkey equipment, custom fixtures, and automated machines, and with product design, visit us at teampipeline.us. Thanks for listening.